So we are in solution chapter. Last class we have discussed about the vapor pressure of liquid solution. So how can we define the vapor pressure in a liquid solution when two volatile liquids are mixed together, or in a liquid, if a solvent is pure liquid and the solute is the volatile component, either gas or liquid, that's okay. Solvent is the one component, it is liquid, and solute, if the solute is volatile in nature, then we have to study the effect of the vapor pressure. So that's what we have discussed. So vapor pressure of liquid solution and also vapor pressure of solution of solids in liquid. So when it comes to vapor pressure, we have to consider the Raoult law. Raoult law only decides the behavior of the vapor, behavior of the solution that consists of volatile matter. Raoult law decides the behavior of the solution that consists of volatile matter. So basically, Raoult law is the partial pressure of a solute or solvent. Partial pressure of a solute or solvent is directly proportional to the mole fraction, as per Henry also states the same thing. But if you made this proportionality into equal symbol, then the constant introduced here is the vapor pressure. Constant introduced here is the vapor pressure. So P01 is the vapor pressure. Say example, I'll explain once again. You are having the solvent, you are having a component, let it be a solvent. So I can name it as 1. If it is a volatile nature, that is, it can easily evaporate. It can easily evaporate. If it is the volatile nature, it must have this solvent must have the vapor pressure. So that is the fixed one, vapor pressure of pure solvent. Let it be P0. Now the mole fraction here, if you check the mole fraction, it will be 1, because you are having only solvent, there is no solute here. You are having only pure component, so the mole fraction must be equal to 1. So the partial pressure must be equal to the vapor pressure. In this case, the partial pressure must be equal to the vapor pressure. But if I add any solute to this solvent, whether it may be gas or liquid or solid, but I'm going to add one solute to this solvent. Because of this solute, this mole fraction must be reduced. Initially, we have pure solvent, so that has the mole fraction of 1. If I add any solute to this solvent, the mole fraction must be reduced. So now, if I say the mole fraction of the solute is x2, then x1 plus x2 must be equal to 1. X1 plus x2 must be equal to 1. So automatically, x1 value will be less than 1 only. X1 value will be less than 1 only. So in that case, the overall vapor pressure is reduced, because P0 is the vapor pressure of the pure solvent. Now, if you add any solute to that, this vapor pressure will be reduced. How much it will reduce? Based upon the concentration of solution X2. So if I add 25% of solute, the solvent will become 75%. X1 will become 75% only. So automatically the pressure will be reduced by 75%. So we have to multiply the total pressure, that is total vapor pressure, with the mole fraction. So if the mole fraction is 1, okay, pure solvent. If the mole fraction is reduced, then we have to multiply it. How much amount will it reduce? So that is given by the partial pressure of first component. This is what the Raoult law says. So if you add any solute to the solvent, the vapor pressure, the original vapor pressure will be reduced. So that is the new partial pressure. So that new partial pressure can be calculated by the product of mole fraction of the solvent and the vapor pressure of the solvent. So that is the Raoult law. Do you have any doubts on this? Do you have any doubts on Raoult law? This is clear, right? 100% clear, right? Any doubts? Or you want me to repeat? If you want me to repeat anything, let me know. You should be 100% clear in this topic, in this area. Because based upon Raoult law only, the solution behavior is fixed. If your solution obeys this Raoult law, it is called as the ideal solution. So based upon the Raoult law behavior, based upon the behavior of the solution according to Raoult law, in that manner only we are going to classify the solution into two categories. One is ideal solution and another one is non-ideal solution. Ideal solution and another one is non-ideal solution. So the name itself clearly says ideal solution. In real time we can't get 100% ideal solution, but maximum if a solution obeys to Raoult law, if a solution obeys the Raoult law throughout its concentration, throughout its entire range, then we can name it as the ideal solution. So the condition of being ideal solution is obeying Raoult law throughout the range, throughout the all the parts. So throughout the entire range of concentration, throughout the entire range of concentration. Entire range of concentration means the meaning. Say example here solvent is, here the solvent is 1, solute is, let me name it as 2. So initially entire range of concentration, it should obey Raoult law. The meaning of that is initially we have solvent as pure solvent only. There is no solute. X2 must be 0 initially. If you add X2 10%, 10% means if you add X2 as a mole fraction of X2 is 0.1, 10% of solute is added, then the 1 is reduced to 0.9. The solvent X1 value is reduced to 0.9. Then if you add further solute, say example, if you add 0.2, that is 20%, if you add, this will become 0.8. Say example, if you add, this is 1, this is 2. If we add X2 as 0.5, 50% is solute 2 means automatically this solvent will become 50%. If you add solute is, then it will become solvent, right? If you add solute is 0.8, then the solute will become solvent. This will become solute. This will become 0.2. So this is the different ranges of concentration. In each concentration, it should obey. In when x1 is equal to 1, it should obey. When x1 is equal to 0.9, it should obey. x1 is equal to 0.99, it should obey. x1 is equal to 0.1, it should obey. For all the different value of concentration, if we check the Raoult law, because Raoult law can be easily verified. We know how to calculate the mole fraction. Partial pressure can be easily measured. We can measure the partial pressure from the total pressure of the solution. If you fit any pressure gauge, you can measure the total pressure of the solution. From that, you can find the partial pressure. So partial pressure you can easily measure. Mole fraction you can easily calculate. Mole fraction you can easily calculate. P1, X1. This two things you can easily get from the solution. From that, if you calculate the value of P0, if you calculate the value of P0, that is the vapor pressure. That vapor pressure must be equal to the original value, because each solvent or each solute, each component has its own vapor pressure. Each component has its own vapor pressure. So when we calculate the vapor pressure from Raoult law, should obey the original vapor pressure of the component. Should match with the original vapor pressure of the component. Is that clear? Is that clear? So when you say example, if I take x1 is equal to 0.9, my concentration is 0.9. In that case, I'm calculating what is my P1, that is partial pressure of 1. So P1 I can measure, x1 I know I can calculate. From that I found P0. That P0 must be the original value. It should not more than or less than the original value, because each component in its pure form has its own vapor pressure value. Okay, so that vapor pressure of each component, we know it already. That is fixed thing. So the thing is, the vapor pressure calculated from Raoult law should be matched with the original value. That is the condition for existence of being ideal solution. That is the condition of being ideal solution. So it should obey the Raoult law, not only when x1 is equal to 1, not only when x2 is equal to x1 is equal to 0.9. Should obey in the all the ranges of concentration. Is that clear? Is that clear? So the non-ideal solution, it doesn't obey. It doesn't obey the Raoult law. Doesn't obey the Raoult law. Doesn't obey means it completely won't disagree with the Raoult law. The value which can be calculated from the Raoult law may be somehow greater than or lesser than the original value. The value which is calculated from the Raoult law may be either higher than or lower than the original value. Is that clear? That is the meaning of doesn't obey the Raoult law throughout the entire range of concentration. Throughout the entire range of concentration. So that is the main difference between ideal and non-ideal solution. Is that clear? Non-ideal solution is clear? Is that clear or not? Okay. Okay. Let me draw the graph. See, this is the mole fraction. This is the mole fraction. So usually we know how to draw the mole fraction for a solution. So any solution containing minimum two quantities. So in this chapter, we are always studying about the binary solution only. Two components only we are studying. So mole fraction means you may have 1 and 2, first component and second component. Say example, this x-axis indicates the x1. This x-axis indicates the position of mole fraction of first component. So this point is x1 is equal to 0. This point is noted as x1 is equal to 0. Initial point. Automatically, this point conveys us that here x2 is equal to 1. So if in a solution, if the mole fraction of first component is 0 means automatically mole fraction of second component must be 1. Okay. The same thing. If I have mole fraction of first component is 1, automatically mole fraction of second component must be 0. Must be 0. So in y-axis, I should take partial pressure. Y-axis, I should take not partial pressure, let it be vapor pressure. Vapor pressure. So what is the vapor pressure? When x1 is equal to 0 means the solution consists of only second component. It consists of only second component. So the entire pressure is because of the second component only. The entire pressure is because of the vapor pressure of second component only. P02. 0, 2. When you have only second component, that is the position of x1 is equal to 0, then the pressure of the solution must be equal to the vapor pressure of second component. Is that clear? Is that clear? Okay, same thing. So if you increase the mole fraction, 0.1, 0.2, 0.3, this value, P2 value increases slowly. And not P2 value, partial pressure of first component. Here it is P2 to the power of 0, right? So I'm going to draw the partial pressure of first component increases slowly. So when x1 is equal to 1, this partial pressure, when x1 is equal to 1, the first component partial pressure will be equal to the partial pressure of first component will be equal to our total pressure. So here total pressure. The total pressure will be equal to partial pressure of first component. Here the total pressure is equal to partial pressure of second component. See, this is, we already explained this graph. I will once more I will explain here. See, when x1 is equal to 0, the total pressure is equal to the partial pressure of second component. When x1 is equal to 1, the total pressure must be, when x1 is equal to 1 means the solution consists of only the first component. So when x1 is equal to 1, the solution consists of only first component. So the total pressure must be equal to the vapor pressure of first component. So if you increases the concentration, of first component, its pressure increases like this. The total pressure goes like this. Okay, it is P1 to the power of 0. Sometimes we don't know P1 value, that is vapor pressure of first component, may be less than vapor pressure of second component. In that the graph will go like this. So we assume that here P1 is more than P2. If that is true, then the graph goes like this. This is the total pressure. This is the graph of total pressure. Now, if I draw the graph for partial pressure, so if x1 is equal to 0 means its partial pressure must be equal to 0. If x1 is equal to 1 means its partial pressure must be equal to P1. So this is the partial pressure of first component. And if x1 is equal to 0 means, x2 is equal to 1 means, partial pressure of second component must be equal to P2. If x2 is equal to 0 means partial pressure of second component is P2. So here I draw 3 lines. One line tells us the total pressure, P1 plus P2. Another line tells us the partial pressure of first component. Third line tells us the partial pressure of second component. So this is the meaning. This is the relationship between vapor pressure and the mole fraction of the solution. So basically we have 3 lines. One line denotes the total pressure, another line denotes the partial pressure of first one, then the third line denotes the partial pressure of second one. Do you have any doubts on this graph? So we already explained this. So this P1 value and P2 value and the total pressure, these 3 only we can measure or we can calculate. This total pressure we can measure. If we know the total pressure, from that we can calculate P1 and P2. So P1 and P2 we can calculate. Okay, and x1 value also, x2 value also we know that we can calculate how to find the mole fraction. So basically by knowing the value of P1 and P2, we can calculate the vapor pressure of first component and second component. So that must be, this is the line when we have to draw the line. If we draw the line like this, means this line tells us that P1 is equal to P vapor pressure of first component into x1. P2 tells us the vapor pressure of second component into x2. So when can we draw the straight line? It should obey the route law. What happened if it doesn't obey the route law? then the partial pressure value may be lower than the calculated value or higher than the calculated value. Maybe it may be like this, it may be like this or like this, and here it may be like this or like this. So this curved line denotes the deviation of the original situation. So the straight line denotes the ideal solution. Non-ideal solution deviates from the ideal solution. That means their vapor pressure must be deviated from the value calculated from the Raoult law. Is that clear? Any doubts? Any doubts, or you want me to repeat anything? Pooja? Okay. So we know in ideal solution it must obey the Raoult law. Then when will it obey the Raoult law? That we should know, right? So in ideal solution, and if I speak about ideal solution, we simply says that it obeys the Raoult law throughout the entire concentration. When will it obey? When will it obey? Say example, we have a solvent. Let it be water. For example, consider the water. Okay, I can name it as A. So in solvent, usually H2O, this is one H2O molecules, and this will be another H2O molecule, and this will be another H2O molecule. Like that, intermolecular force, intermolecular bonding is there like this. Because of that intermolecular force only, it exists as the liquid. We know about intermolecular force, right? The force between first molecule and second molecule or intermolecular bond. So the intermolecular relationship or intermolecular force or attraction is intermolecular attraction of A and A. Let it be, I can calculate, I can make it as the intermolecular force or intermolecular attraction of A and B. So if I calculate it in Newton, let it be FA, intermolecular force between A and A. So when you have only pure liquid, pure H2O, in that the intermolecular force must be equal to something, that is intermolecular force between water and water molecule. Now you are going to add a solute. So let the solute is the sodium chloride. Let the solute is sodium chloride. So I can name it as B. Now the intermolecular force of B to B, then we can name it as FB. Okay. So that is sodium chloride and another sodium chloride and another sodium chloride. Like that, the force will be there. Is that clear? So one molecule of sodium chloride is bonded with another molecule of sodium chloride. Like that, we have the solute. Now, when the solvent and solute are mixed together, so this is A, this is B. Now we have the component AB, right? We have the component solution AB, right? Solution is AB, right? Like this. That means when A and B are mixed together, it is not reacted. It is not chemically reacting. I'm not saying H2O is reacting with sodium chloride. This sodium chloride is dissolved in the water. That means H2O molecule won't be disturbed. Another H2O molecule is also it also won't be disturbed. But in between two H2O molecule, the NaCl molecule will be placed. That is called a dissolving. Dissolving is something different. Reaction is something different. Reaction is, say example, if I say sodium chloride and water, HOH, what will happen? Hydrogen and chlorine is reacting together and it forms HCl, and sodium and OH will it forms NaOH. If this is the output product, that is called a chemical reaction. That is called the chemical reaction. We are not discussing about the chemical reaction. We are not saying this H2O and sodium chloride chemically reacted together. What we are saying here sodium chloride is dissolved into the water. Is dissolved means the molecule of sodium chloride will be placed in between two molecules of H2O. Two molecules of H2O. Is that clear? Is it clear? So in that case, now the intermolecular force of solution, that is A, B, A. See here A, and after that one B, after that A. Now if I say the intermolecular force of solution F, or let me make this. Here it is F A to A. Here it is F B to B. Here if it is F A to B, B to A. If all these three are equal, or F A to A is equal to, that is the intermolecular force of solvent is equal to the intermolecular force of solution. If the adding sodium chloride, if it doesn't disturb the intermolecular force of the existing solvent. So we have solvent, it has its own intermolecular strength. If we add sodium chloride, in between two water molecules, if the intermolecular strength of existing solvent is not disturbed, that means the new intermolecular strength is equal to the old intermolecular strength. Old intermolecular strength is strength between A and A. New intermolecular strength is strength between AB, strength between AB, If these two are equal, if these two forces are equal, by adding the solute, the intermolecular strength is not disturbed, is not increased or decreased, then it is called ideal solution. Then it must obey the Raoult law. Is that clear? It obey the Raoult law. Okay. So automatically, what is non-ideal solution? The intermolecular force of the solution is either greater than or less than the, ideal solution, is either greater than or less than the intermolecular force of solvent, then it become the non-ideal solution. Okay, make a note of this. One more thing we should remember here is, if you add any solute, because of that solution reaction, there should not be any heat released or absorbed. That means enthalpy change of the solution, enthalpy change in the reaction must be equal to 0. Because of the dissolving process, there should not be heat released or absorbed. Okay, and the volume of the solution also, the change in volume of the solution must be also equal to 0. The volume of solution, it should not increase. Say example, you are having a cup of water. If you add 1 teaspoon of sodium chloride to it, whether the volume is increased? No, the volume is not increased. We know that, right? So the change in volume must be equal to 0. Say example, if you add instead of adding salt, if you add a stone, 2 drops of stone or 2 stones to the water, automatically the volume of the entire content is increased. That means the dissolving process is not 100% correct, is not 100% ideal. Some of the stone particle may dissolve into the water, some of the stone particle won't dissolve into the water. So automatically what will happen? The water level rises when you add stone to the water. But when you add small amount of sodium chloride to the water, what will happen? The sodium chloride is completely dissolved into the water. Because of that, the volume of water won't increase. So in a pure ideal solution, there should be no heat release or no heat absorption. That is, the enthalpy change must be equal to 0, and also volume change must be equal to 0. Is that clear? Is that clear? So for ideal solution, if we mix n hexane and n heptane, n hexane, so methane, ethane, propane, butane, pentane, after that hexane. N hexane and n heptane, if we mix these two components, then that must be the ideal solution. Okay, because both are hydrocarbon only, both are near to that. Here only six carbon, here 7 carbon. So the intermolecular force won't be changed because of adding heptane to hexane or hexane to heptane. There is not much change in intermolecular force. And also see here bromoethane and chloroethane. Bromoethane and chloroethane. So solution of bromoethane and chloroethane. Benzene and toluene. All are hydrocarbon. See here, hexane and heptane is hydrocarbon. Benzene is hydrocarbon. Toluene is also hydrocarbon. What is benzene? Benzene is C6H6. Toluene is C6. Instead of one hydrogen, you have to add one methyl group. That is toluene. Hexane, you know, hexane is 6 carbon with 14 hydrogen. CnH2n plus 2. Here 7 carbon with 14 plus 2, 16 hydrogen. Ethane, you know, ethane we know, right? C2H5. Instead of one hydrogen, here we have bromine. Here, instead of one hydrogen, we have chlorine. So look at the structure, look at the molecular formula, both are nearly similar. So in that case, if we mix, the intermolecular force won't be disturbed. So make a note of this and read it. Read 2.5.1. Non-ideal solution means when a solution doesn't obey a Raoult law. Doesn't obey a Raoult law. Okay. When will not it obey the Raoult law? When it won't obey the Raoult law? Say example, the solvent in the previous case, the solvent, the intermolecular strength of solvent and the solute is BB, and the solution must be A, B, A. See, this is the solution. The intermolecular strength of solution, if the intermolecular strength of solution is either greater than or less than intermolecular strength of solvent, intermolecular strength of solvent, then it won't obey the Raoult law. I will explain why. Intermolecular strength of solvent. Okay, solvent is AB. Solvent or AA. Okay, so see what is the meaning of doesn't obeying Raoult law? If the solution doesn't obey Raoult law means then the vapor pressure calculated from the Raoult law is varying from the original value. That's the meaning, right? So when the solution doesn't obey the Raoult law throughout its entire concentration, then the vapor pressure of the solution, that is the original vapor pressure, is either higher than or lower than the calculated value, higher than or lower than the value predicted from Raoult law. So whatever the value we found from the Raoult law, that must be different from the original vapor pressure. It may be either less than or higher than the original vapor pressure. So the value predicted by Raoult law. Okay. Now, when will the vapor pressure of the solution is high, original vapor pressure of the solution will be varying from the Raoult law. Whether, so I can say that I said that the vapor pressure of the original solution is either higher than or lower than the theoretical value. So the whatever the value we found from the Raoult law is the theoretical value. The original value is the value given that the measured value, that is the original value, right? So why that original value is varying from the or is deviating from the theoretical value? Because of this reason. Say example here, when the solute is added to the solvent, the solution becomes like this. It will become A, B like that. So AA is the solvent and BB is the solute. So in between solvent, solute particle is added. Now the original solvent is like this. For example, if intermolecular strength, see, when intermolecular strength of AA, when the intermolecular strength of AA or intermolecular strength of ABA, that is solution, if the intermolecular strength of solution is less than the intermolecular strength of solvent, what will happen? Solvent is the original form. So I'm adding a solute. Because of that solute, the intermolecular strength is reduced. If the intermolecular strength is reduced, then what will happen? The solute or solvent can't be in that bond. It can't withstand the bond, right? Because the bond only makes the component in the liquid form. Because of the bond strength only, the component exist in the form of liquid. Is that clear? Do you get the point? Because of the bond strength only, the component either A or B exist in the liquid form. If the component strength, the bond strength is reduced, it may not attach with that bond. It may not attach it properly. So there is a chance of molecules escaping from the, escaping of molecules from the solution. If the molecules can't be withstand in the bond, if the molecules cannot be lying inside the bond, so it tries to escape. If it tries to escape, means it should escape as a gas only, because once it leaves the bond, it must be in the form of gas. So I'm adding a solute. Because of the solute, the intermolecular strength is reduced. So some of the molecules may try to escape. So they are escaping in the form of gas. So that escaped gas resides at the top surface of the solution. So they add the extra pressure. Is that clear? So some of the molecules escapes from the bond. So it adds the extra pressure. So in this case, I'm writing here, in this case, the vapor pressure of the VP is the vapor pressure of the solution is greater than the vapor pressure of the solution found by Raoult law. Solution, Raoult, I can write like this. Okay. Or else you can write vapor pressure of the theoretical vapor pressure. Theoretical value. This is the actual value. Vapor pressure of the actual value is greater than the vapor pressure of theoretical value. Why it is greater? Because some molecules, maybe solute or solvent, escaped from the bond. Why it is escaped? Because of the solution, the intermolecular strength, the original intermolecular strength is reduced. So this variation, this deviation is called as the positive deviation. This deviation is called as the positive deviation. The value, the original value is varied from the, is positively deviated from the theoretical value. So we have in the deviation, in the non-ideal solution, we have two types. One is the solution which shows the solution which shows the positive deviation, and another one is the solution which shows the negative deviation. Now negative deviation you can easily understand. Intermolecular strength of ABA solution, that is intermolecular strength of solution, if it is greater than the solvent, if it is greater than the solvent, then more molecules will try to attach it with the bond. It won't escape. So it automatically reduces the pressure. So pressure is because of the gas resides outside the top surface of the solution. When the intermolecular strength is high, the amount of gas molecules, the number of gas molecules in the top surface will try to attach with the bond. Will try to attach with that bond. So automatically pressure is reduced. Automatically pressure is reduced. So that is negative deviation. So there are two kinds of deviation. One is positive deviation and another one is negative deviation. What is positive deviation? When the intermolecular strength of solution is less than the intermolecular strength of solvent. When the intermolecular strength of solution is less than the intermolecular strength of solvent, some of the molecules escapes from the bond. Because of the escaped molecules, it adds the extra pressure. It adds, we have extra pressure. Make a note of this. So now, positive deviation. How can we express the positive deviation in graph? So we already tried it. So in x-axis, you should draw mole fraction. In x-axis, you should draw mole fraction, and the initial point denotes the x1 is equal to 0. That is, solvent is equal to 0. The solution consists of only second component. In that case, this is the vapor pressure of the solution. Vapor pressure of the solution. So when x1 is equal to 0, when x1 is equal to 0, the total pressure of the solution must be equal to vapor pressure of second component. When x1 is equal to 1, that means you have only pure solvent. There is no solute. First component is pure, second, there is no second component. So in that case, the total pressure must be equal to the vapor pressure of first component. Vapor pressure of first component. So this line tells us the total pressure of the solution. This line tells us the total pressure of the solution. So this line found from the Raoult law. This line found from the Raoult law. So total pressure of the solution, that is P1, partial pressure of 1 plus partial pressure of 2. And if we draw the partial pressure of first component itself, so when x1 is equal to 0, partial pressure of first component is 0. So if we increase the concentration, partial pressure of that component is automatically eventually increases. Same for second component. Same for second component. If the partial pressure of second component is 1, so if the concentration of the mole fraction of second component is 1, then the partial pressure of the second component must be equal to its vapor pressure, must be equal to the vapor pressure or total pressure. Then if you decrease the second component, mole fraction of second component, automatically the graph goes like this. So this graph tells us the partial pressure of second component. This graph tells us the partial pressure of first component. So this is the graph which can be drawn by using the values calculated from the round law, by using the values calculated from the round law. Now the deviation. Now the deviation. So if we have positive deviation, positive deviation means the original pressure of the solution at this point and this point is not problem. Is at this point and this point is the pure. It is in the form of pure. Okay, here we have only pure first component, pure second component. At this point we have only pure first component. So this point and this point we don't need to calculate, we don't need to verify. But in between these points, the value will eventually increases. The original value. This is the vapor pressure of solution. And this is the positive partial pressure of first component. More than that, the calculated value. Then this is the partial pressure of second component. So the black color line tells us the positive deviation. From the normal value, it is somewhat high. Okay. So why is this happen? Because of the reduction in intermolecular strength. Why? Because of the adding solute to the solvent. When we mix two components, if the intermolecular strength is reduced, automatically more amount of gas molecule escape. If more amount of gas molecule escapes, then the escaped molecules will add the extra pressure. Will give the extra pressure. So the original pressure is deviated from the theoretical pressure. Hope you understand. Then the negative deviation, the same thing. How to draw the negative deviation? The same graph. This is the example for negative deviation. So positive deviation, for example, in positive deviation exhibited by mixture of ethanol and acetone. Mixture of ethanol and acetone exhibiting the positive deviation. See why? When we have ethanol, so in ethanol, it is ethanol CH3 CH2 OH. It is one ethanol molecule, and this will be the another ethanol molecule CH3 CH2 OH. This is the another ethanol molecule. Now these two molecules are connected by the hydrogen bond. Because the hydrogen from first molecule is bonded with the carbon of the second molecule, and the same way hydrogen of this molecule is bonded with the carbon of the third molecule. Like this bond strength is happening. So here the intermolecular force is because of hydrogen bonding. Now if you add acetone to it, this is ethanol. If you add acetone to this, acetone is acetone CH3 CO CH3. This is acetone. When ethanol is added with when acetone is added with the ethanol, or ethanol is added with acetone, what will happen? Sometime, so CH3 CH2 OH, in between this two ethanol, this CH3CO CH3 will be placed. So it weakens the existing hydrogen bond. Here it weak the hydrogen bond. Okay, so what will happen? Some of the bond may be broken. So because of that, either ethanol or acetone escapes from the solution and it adds the extra pressure. Is that clear? Is that clear? Yes, sir. And another example, acetone with carbon disulfide. Acetone with carbon disulfide. What is carbon disulfide? Acetone is CH3COCH3. Carbon disulfide is CS2. Carbon dioxide we know, it is carbon disulfide. Okay, if you add carbon disulfide to acetone, so what will happen when the bond between acetone and carbon disulfide, bond between acetone and carbon disulfide is the bond strength of acetone and carbon disulfide is less than the bond strength of acetone or bond strength of carbon disulfide. Okay, so if you mix these two things, the intermolecular strength is reduced. So it results the positive deviation. Now come to negative deviation. The same thing. So this is the original value. So total pressure of the solution. And this is the partial pressure of first component. And so this is x1 is equal to 0, x2 is equal to 1, x1 is equal to 1, x2 is equal to 0. This is the partial pressure of second component, P2. What is negative deviation? The intermolecular strength is increased by adding the solute to the solvent. The intermolecular strength is reduced. So only less amount of gas molecules resides at the top surface of the solution. So it decreases the pressure. So it results the negative deviation. So the original pressure is less than the theoretical pressure. Is that clear? Okay. Now here the example. What is the example? So in the previous problem, I said that the intermolecular force because of hydrogen bond. In the ethanol and ethanol, we have hydrogen bond. So this hydrogen bond is weakened because of adding CH3COCH3. Okay. At the same time, if you add in the hydrogen bond, if you add any nitrogen to it, say example, take phenol and aniline. So what is phenol? Phenol is basically C6H5OH, benzene with alcohol. Aniline is same thing, C6H5NH3, NH3 is the ammonia. In that because of instead of one hydrogen, C6H5 is added, benzyl group is added. Now when these two are mixed together, this hydrogen is bonded with the nitrogen. Of the aniline group. So when hydrogen and nitrogen are bonded together, so in the previous case only hydrogen and carbon are bonded together. Here hydrogen and nitrogen are bonded together. When hydrogen and nitrogen are bonded together, the intermolecular strength is increased. So this results the negative deviation. And another one example is let me erase this. The next example. In acetone, CH3 COCH3. This looks like this. Acetone looks like this. CH3 C double bond O CH3. If chloroform is added with acetone, what is chloroform? CHCl3. So when chloroform and acetone are added together, when chloroform and acetone are added together, what will happen? What will happen? There will be the bond between oxygen and hydrogen. There will be the bond between oxygen and hydrogen. So it also increases the intermolecular force. Hydrogen and hydrogen, intermolecular force is increased. Because of oxygen and hydrogen, intermolecular force is increased. So if we increase if the solution increases the intermolecular force, it results the negative deviation. That means the escaping tendency of molecules is reduced. So automatically less amount of molecules only will be residing at the surface of the water, at the surface of the solution. So this reduces the pressure. So that causes the negative deviation. Hope you understand. Any doubts? Any doubts? Okay. So make a note of this.